Hello, in this session we will treat ultrafast laser applications. You are well aware what we can do with data in communication technology in transferring terabits per second through fibers and organize internet communication in the way we are used to it today. Now imagine you could project this flux of data, this precision of millions of events per second to power levels at which we really can have direct action, ablation, modification of materials. So this has the potential of really revolutionizing our production technology if we are able to scale the power of such processes and lasers. In the summary, you see here a list of issues we will handle. So we will start with the definition of ultrashort, ultrafast lasers, the interaction of such lasers with matter from the physical point of view. Then we will get into the ablation process and look at some applications, application examples, for instance, refractive index modification, two-photon lithography, microscopy. As an outlook, we shall take a look at potential applications in future science and new domains of ultrafast lasers all the way down to attoseconds, which is 10 to the minus 18 seconds. Now let's take a look at the definition of what we understand by ultrafast. There are two views. One is the materials processors view, which defines the threshold between an equilibrium coupling of electrons and phonons, and if we get to shorter times, the need to separate the two events, so to separate the coupling to the electrons from the subsequent coupling to the phonons. A laser engineer's, physicist's point of view is very simple because we are simply able to build such lasers if we apply mode locking. Then we can get down to pulse lengths of a few cycles of the wavelengths used, which is in visible light lasers something like 3 to 5 femtoseconds. So in the language that we will use to describe the processes, we will have the pulse peak power, which is defined by the peak of each individual pulse. We will talk about the repetition rate, which is simply 1 over the time distance between two pulses. Of course, each pulse will have an energy, which is the integral over the time of that power, and we can identify an average power, corresponding average power, which is just the time average of all the delivered energy. A little on the fundamentals of ultrashort lasers. If we apply an ultrashort pulse to a surface, we face the following situation. In this view graph on the left, you can see the temperature on a surface, and on the abscissa we plotted the material depths. So here's the surface and here's the material depths. And of course, as you know intuitively, the temperature will increase on the surface and it will take some time for the temperature to diffuse into the material. So we will have a gradient of temperature into the material. Now the important thing, which you also can look up in the heat conduction video, is that the temperature scales with the root of the time and the penetration depth, which is the instant where the temperature dropped to about 1/10 of the temperature on the surface. The penetration depth of the temperature scales with the root of the time. To be exact, it's the root of 4 times the thermal conductivity times the time. So, with the time, this curve will move into the material. We will have higher temperatures and higher penetration depths, or if we go to the other end, we will have smaller temperatures and smaller penetration depths with corresponding shorter times. Now, if we want to take a look at the ultrafast laser applications, we take a look at the dependence of the thermal penetration depth on the irradiated time, which we see on the plot on the right. Here is plotted the thermal penetration depth over the pulse duration. As I said, it scales with the root of the time, and it's plotted for two different materials, a high thermally conducting material aluminum and a less thermally conducting steel. But from the order of magnitude, you can see that if we want to go to ultra-fast lasers of the range of about 10 to the minus 12, which is a picosecond, about a picosecond lasers, then we get thermal penetration depths of the order of about 10 to the minus 8 meters, which is about 10 to 50 nanometers. If theoretically we ask the question, what would be the time of irradiation of a surface such that we get an evaporation of only one layer of atoms, and the layer below that layer doesn't even know that the layer above it was blown away with 10,000 Kelvin? The answer from this simple analysis would say about a few tens of femtoseconds. So if we plot this in our graph here, you can see that about 10 to the minus 15 seconds is a femtosecond. So a few femtoseconds, few tens of femtoseconds will bring us to the order of an atomic diameter in terms of thermal heat penetration. The fascinating thing about this is that we are able to build lasers of that pulse length. However, the full truth is not as simple. If we look at real materials, at the example of metals, then we have to face an optical penetration depth, which of course scales with the speed of light. The energy is deposited in the material at the speed of light. So it is much faster than the thermal penetration, and this limit tells us that it makes sense in metals to process maybe only thermal penetration depths of the order of a few tens of nanometers, which brings us to pulse durations of the order of 10 to the minus 12 seconds. So this is the reason why we talk about ultrafast lasers with pulse lengths in the range of a picosecond or a few picoseconds. And for materials processing, it doesn't really make sense to get a lot below that value. As a consequence, we face a situation in which the energy coupling is divided in several domains. They are listed here on the left, and very schematically it is plotted an electron system and a phonon system. Think of metals in this application. So the free electrons in a metal will follow the incident field almost instantly. So we will have typical coupling times of a few tens of femtoseconds. So the electrons are heated very quickly. Then they collide and they thermalize. So the electron interaction time is about 10 times of that value, something like 100 femtoseconds. Only after that there will be the transition from the electrons to the phonons, to the lattice of the metal. So this takes about 1 picosecond, and the thermalization of the phonons will take about 100 picoseconds. So those are the 4 steps in the energy coupling process. If we look at the example of metals in the interaction with ultrafast lasers, and you may realize that using a sub-picosecond pulse, maybe a 200 femtosecond pulse, we will have thermalized electrons, so the electron temperature will be definable. However, we don't have any energy in the lattice yet. So the laser pulse will be off for quite a long time until the energy diffuses from the electron system into the phonon system. It is visualized on the right-hand side, where you see the free electrons here indicated by these little dots, and the lattice in a very simple spring model with the nuclei here in black. So at first we shake the electrons, they thermalize, and then they collide with the lattice and transfer the energy into the lattice. But this is taking place only quite a time after the laser pulse is off again. This is visualized here in this model where we plotted the interaction and the corresponding temperatures for typical processing values for a picosecond laser. So in this case here, the pulse duration is 1 picosecond, which means the temperature of the electrons follows the increase of the laser pulse quite directly until the pulse is off. Then the temperature does not increase anymore. And if the pulse is off, the electrons cool down, and with that cooling down, they start to transfer the energy to the phonons, which is the green curve here. And in this case, you see the delay of the energy coupling between the electrons and the photons quite directly. Correspondingly, the process of evaporation starts only if the lattice really feels the temperature, and this takes place after about a few picoseconds. So after the pulse is off, then the phonons will really heat up and start the ablation process. And again, the ablation, of course, diminishes with the decrease of the phonon temperature. So the ablation process takes place something like up to maybe even a nanosecond. If we prolong the pulse length, take a longer pulse, in this case of 1 nanosecond, then you don't see really a difference between the two temperatures of the phonons and the electrons anymore. So two-temperature model is actually only necessary for descriptions of pulse lengths in the ultrafast domain, which is below about a picosecond, a few picoseconds. If we come to applications, there's one very important thing to consider. With these high intensities that we can provide by ultrafast lasers, we are able to stimulate two-photon processes or even multiphoton processes. You see the principle sketched up here. What we do is that we stack two photons of a relatively low energy on top of each other to provide a sufficient energy for a transition, for an excitation in a material state. And in this absorption process, we have now a intensity threshold which scales with the number of photons required for the excitation. And the probability for this process scales with the power of the number of photons needed. As a consequence, the threshold is defined somewhere depending on the process. And if we look at our typical distribution of a lateral intensity behavior of a pulse, of a laser pulse, usually we talk about a Gaussian distribution indicated here in this green curve. And if we look at these nonlinear processes, you see that depending on the threshold, the spatial domain will be much smaller compared to the linear processes. And as a consequence of that, if we process, for instance, transparent material, we will have no absorption when the intensity is below a corresponding threshold. However, if we reach it, we do have the absorption, multiphoton absorption, but only where the intensity is sufficiently high. So this can be tailored very precisely to rather small areas depending on the threshold of the process. So to say, we cut out of the classical Gaussian beam caustic only a very small portion depending on the intensity threshold. And that increases local resolution depending on the ratio of intensity to the threshold intensity of the process. Let's look at some examples where we use these facts. At first, I would like to show to you a very simple view to, so to say, rehearse what we have talked about so far in a very simple matter. If you look at a typical material system, it is consisting of atoms. These friendly guys here are supposed to be atoms. And if we use thermal processes like in cutting, what we do is we apply the laser from the top, we heat the atoms, and then we find the thermal penetration depending on the root of the time, which leads to the fact that we get a temperature increase in the surface and the material itself. And then after exceeding the melting temperature, we can blow out the molten material with a gas jet and get a ablation or a cut or a drill. And the resulting geometry will depend on the recast of the resolidified material. In ultrafast processing, in the limit, we have a very different process. If we apply femtoseconds, we just address a few atoms, few layers of atoms, and they vaporize immediately, and the heat affected zone is very, very small. It depends on the gradient, and in these short pulses, typical values, if we talk about picoseconds of melt formation thickness, are somewhere below a micron in metals. And as a result of that, we get extremely high precision in these ablation processes. Here you see 3 examples where we applied picosecond lasers for steel, ceramics, polymers, and as you might imagine, it doesn't really make a difference which material we process, as long as we localize the energy in very thin surface layers and allow the short times to ablate the material so that the heat effect on the environment of the processing zone becomes negligible. And in the metal application here, you see very clearly that there's hardly any melt visible, so we get very high precision of the order of a micron, and typical values at this point may be interesting to mention. Of pulse rates for such lasers are something like 20 million pulses per second, so this is a very high speed, very low pulse energy. So portion by portion is ablated very precisely, but very fast with very fast repetition rates, high repetition rates, so that we get these macroscopic ablation rates, scaling the laser power, and then get to macroscopic applications in production technology. As an example, I would like to show you a vision which is relevant maybe for all of us, because we all use these wonderful advances of air travel. However, we are all aware that this takes a lot of energy, and it would be wonderful to reduce the friction and the energy consumption of airplanes. This can be done. This is a study from NASA, which shows you that depending on the position on an airfoil, we get turbulence, especially in the low pressure areas. And these turbulent flows mix with the bottom flows so that we get real big turbulence in the tail of a wing. Now this can be reduced, and it has been calculated that if we would be able to apply very many thin holes of an order of maybe 100 micrometer in diameter in that airfoil, then we could suck off these turbulent flows. We could make the flow closer, stay closer to the wing, and thus reduce the formation of turbulent flow in the rear of the wing significantly. Here you see a picture of such perforating processes. We would need a second layer, but this can be done very easily in the air wing construction. So the important thing is seen here on the upper right corner of the picture, because if we do that, we will be able to reduce the fuel consumption by up to 15%. And that would really be something. What we need to do for that is we need to drill a lot of holes into these air wings. And by a lot, I mean something like 100 billion per airplane. So we need high power, ultra fast lasers, which make the process scalable in order to perform such perforation on an industrial level. We would need something like 10,000 holes per second in order to get this done in a limited, proper time. On the right-hand side here, you see a picture of 196 holes which are drilled simultaneously in a process with a split beam. So there are several ways of scaling the power application to such processes. Definitely we would not drill one hole after the other, so it would take more intelligent process designs in order to do such applications. Well, some more applications on a very different level. In this case here, we modify the index of refraction of glass, sapphire, other transparent media with ultrafast lasers, and in a subsequent second step, as you can see here, we etch the so irradiated zones, areas. In this case here, it is the formation of a waveguide in a glass. In this etching process, which sounds a little environmentally unfriendly, but it is not. This potassium hydroxide solution doesn't harm anything, so it is very environment friendly. And as a result, we get extremely precise structures which we can etch out of transparent media, again with these multiphoton absorption or nonlinear absorption processes in glass. You see some examples here, some gear or some mock-up geometries. So aspect ratios up to 1000 can be achieved, cutting curve widths of about 1 micrometer, so extreme precision in glass with selective laser etching. A final example on application of such lasers is two-photon lithography. Again, we make use of multiphoton absorption. Here in the upper left picture you see again this dependency on the threshold, so we get a very narrow, small area which will be processed because we focus it only, not only in the lateral dimension, but only in the direction of propagation of the laser. We call it a voxel, so we can have very precise and small voxels. On the right you see an application in the 3D printing out of a liquid polymer, in this case of a vessel, a blood vessel, a scaffold, which later will be used to grow in original biological material. In microscopy, we also can make use of this high precision of two-photon absorption processes. As an example, I show you finally the laser scanning microscope. You may be familiar with it. On the left side you see the picture sketch of a classical electron scanning microscope where we irradiate a volume, a complete volume, and select a certain point in a layer by placing a pinhole in front of the detector. So we select only a very specific focused depth in which we identify the fluorescence or the emitted light out of the sample, and then we scan this point over the line, then over the layer, and then layer by layer over the depths of the material, scanning microscope. If we use two-photon excitation, we don't need the selection of the pinhole because we excite only in a very small voxel, as I showed you before. To have this in more direct view, you see here the corresponding images of a confocal laser scanning microscope illumination, where we illuminate a total line throughout the depths of the sample using the two-photon microscope. It's just this tiny voxel that we illuminate and can resolve in the microscope. So this concludes actually this lecture on ultrafast lasers and applications. Needless to say that people strive to scale the laser power. Presently, several kilowatts have been demonstrated with pulse lengths below 1 picosecond and pulse rates up to 20 megahertz. So this scaling process takes place, and it will open a total new domain of applications. Just for your vision for applications in the outlook, in scientific applications, so the time normal using frequency combs and getting really a big step in the resolution in time measurements has been granted a Nobel Prize in 2005. So this is only possible with ultrafast lasers. Then we can focus these high intensities into a gas jet, and by nonlinear frequency conversion we get a whole series of harmonics of the incident laser light. So we can increase the photon energy by this higher harmonic generation and reduce the wavelengths down to the near X-ray region. This then, of course, is coherent radiation, and if we look at coherent X-rays, this would be one way to go. The next example is pretty future-oriented. It is the formation of attoseconds. And as you have seen, we need very short wavelengths for that, because we are limited by the number of cycles per pulse. In the visible, it's about femtoseconds. So if you want to go to attoseconds, we need to go to the UV. And this is actually the same challenge as we can provide solutions for with the gas jet higher harmonic generation by having these short wavelengths. And now we can use these wavelengths, these short wavelengths, to make attosecond pulses. The way this works is that with these high electrical fields, we distort the classical binding of the electrons and shovel the electrons up to higher levels so that the resulting emission goes into the deep UV or even X-ray region. The last example is the formation of plasma filaments. In this case here, we focus laser radiation and generate a string of microplasmas by Kerr-lens focusing and plasma defocusing. It's a repetitive process of the formation of such plasma pearls, which make the air ultimately conductive, so that in this application here, which is a gas discharge, we will have a clear path of the discharge. People think in the vision of guiding lightnings at airports to corresponding places and allow airplanes also to fly in thunderstorms and lightnings without any danger. So, we can make wonderful things with ultrafast lasers. This ability of projecting the density of data as we know it from communication and information technology from our computers into power applications where we can directly use the bits for ablation, for materials processing, that may lead to a new era of using this form of energy in industry and industrial production. Because if you think about it, the industrial revolutions are characterized by the form of energy. The first one was mechanical energy, steam energy. The second one was electricity. And maybe now we face a new era using photonic energy.